So it's time to start. Our next speaker is Seongjeong Kim from the Jilin University. So you can start.
Thank you very much for introduction. And first of all, thank you for giving me an opportunity to give a talk in the conference. And let me start my talk. Today, we'll talk about the Kaufman-Skein module of the connected sum of S1 times S2 and S1 times S2. Firstly, let us remind some basic notions, and then in the second part, we will show some results obtained by calculation. And from the calculation, we can get one important property of KBSM. And that is the plan of our talk. Firstly, let us start with the Skein module. Actually, Skein modules were introduced by Treff and Pristke independently. And there are many kinds of Skein modules, but the Kaufman-Skein module of three manifold is the most extensively studied object in this theory. Then, what is the Kaufman-Skein module? First, let's take an oriented three manifold M, and let K be a commutative ring with unity and A a fixed immutable element in K. And then let's take LFR with a set of isotopic classes of unoriented framed links in M, including the empty ring formally, modular topological equivalence. It means ambient isotopy. Here, framed links we can understand as a ribbon, embedded ribbon in M. And let's take free K module generated by LFR, and we denote it by K LFR. And now let's note by S2 infinite the submodule of K LFR generated by all Skein expressions of the following forms. Here, this state of framed links is obtained inside a small three-ball in three manifold. Then the Kaufman-Skein module of M is the quotient module of K LFR, quotiented by S2 infinite, and we will denote it by S2 infinite M KA. For brevity, if when K is equal to Z a to the plus minus 1, then we will denote it by S2 infinite M simply. Then one of basic result, but important result is the following: that F be an oriented surface and I an interval, 0, 1 interval, then the Kaufman-Skein module of F times I is a free module generated by links in F, including the empty link with no trivial components. It means if a three manifold is the product of a surface and the interval then one can simply project the links onto the surface and work with their link diagrams, splicing or remove a trivial component, and we multiply our coefficient like that. But I said this one is the simplest case, but it is important because in the case of second surface, we can get an algebra structure. In particular, we can define the multiplication of elements in the KBSM. The Kaufman-Skein module of F times I can be equipped with an algebra structure where the empty link is the identity element and the multiplication of two elements is defined by placing L1 above L2. For example, for the torus F, we take 3 link on F 10, 01, and 11 curves. Then the multiplication in KBSM, sorry, this is a KBSM of torus times I is the analysis times I can be presented by such a diagram. It means since 01 is the first is placed in the first place, so we put it on the top, and then we take 01 and then 11 curve below the others. And finally, let me introduce one more notions in KBSM theory. It is the relative Skein algebra. The definition of relative Kaufman bracket Skein module is similar. Let M boundary M be an oriented manifold with boundary, and we take 2 unframed points on boundary M, and K is be a commutative ring with unity with a fixed element, invertible element A. Then L, FR to M be the set of all relative framed links in M, boundary M considered up to ambient isotopy, keeping boundary M fixed, such that L intersection boundary M is equal to boundary L, and which is the set of framed points. Just in case, let me show one example. For such a second surface, I mean, disk with 2 holes times 01, then we take 2 framed points. Here, the framed points are, is an interval on boundary M. So here we take 2 boundary points. Then the relative framed link is the link which has such that if it has a boundary, then the boundary must be on X1 and X2. And if we project on the disk with 2 holes, then we can get such a diagram for relative framed link. And the relative KBSM is defined, can be defined similarly to KBSM without boundary and framed points, but we collect all possible relative framed links quotiented by the Kaufman bracket Skein relations. And now, to calculate KBSM, we require 2 important properties. Firstly, if N is obtained from M by adding 300 to M, and I is the associated embedding, then the induced homomorphism I star from KBSM of M to KBSM of N is an isomorphism. It means to attach 300 to 3 manifold does not change the KBSM. And second property is the following: that M and boundary M be a 3 manifold with boundary, and gamma is a simple closed curve on boundary M. And let N be the 3 manifold obtained from M by adding 2 handle along gamma. Then there must be an associated embedding from M to N. Then the induced homomorphism I star from KBSM of M to KBSM of N is an epimorphism. Moreover, the kernel of I star is generated by the relations either by 2 handle slidings along gamma. Or precisely, if LFR, if we denote, please forget. Sorry. The K-best-M of N is isomorphic to the K-best quotient module of K-best-M of M, quotiented by submodule generated by L minus SL gamma L. Here, SL gamma L is the result of hand sliding along gamma. It means if we have a gamma here and we have a L, then this blue curve should be SL gamma L. And here we can see that if we attach the two handles along gamma, then we get the relators from the two handles. And from those two properties, we can get such a strategy to calculate K-best-M of three-manifold. We know that three-manifold can be obtained from attaching two handles along the closed curves on boundary of handle body, and then we attach three handle additionally. But we know that three handle does not change the K-best-M, so let's forget about three handle. Then from the previous properties, we can see the following fact. The K-best-M of M is isomorphic to the quotient module of K-best-M of handle body, genus and handle body, quotiented by the handle sliding relations along gamma 1 to gamma n. But here, let us consider handle bodies like that. If we have a genus n handle body, then it can be considered as a second circuit, the product of disk with n holes times 0, 1. So we can change our expression like that. It is isomorphic to the quotient module of K-best-M of this second surface quotiented by this one. But in the beginning, we saw that the K-best-M of second surface is free module generated by links on the disk. And in the same time, it has an algebra structure. So roughly speaking, we can say that to calculate the K-best-M of a three-manifold, we find generators for this K-best-M from the handle body, and we can find the relators from the two attached two handles. And from this strategy, we can get such a result. By Host and Prisky, it is proved that as a module over K equal to G, A to the plus minus 1, the K-best-M of S1 times S2 is isomorphic to this decomposition of the modules with the free part and such a torsion part, where the free part is generated by empty link. And now let's start to calculate calculate the K-best-M of our main object S1 times S2 connected sum S1 times S2. Following the strategy, let's first let's understand how it can be obtained by from handle decomposition. We know that S1 times S2 connected sum S1 times S1 times S2 can be obtained by attaching two handles along two closed curves gamma 1 and gamma 2 to the genus 2 handle body. Then firstly, let's understand the generator obtained from this from the K-best-M of genus 2 antibody. Then the K-best-SAM of genus 2 antibody is a free and infinitely generated GA to the plus minus 1 module, whose standard basis consists of monomers of the form A1 I to the I, A to the I, A to the K, where A1, A2, A3 are homotopically non-trivial curves on disk with two holes, illustrated here. A1 is the closed circle surrounding this hole, and A2 is the closed circle surrounding this hole, and A3 is the closed circle surrounding both of holes. And for example, we have such a link on the disk, then this should be presented by a multiplication of A1, A2, A3, A1 square, A2, and A3. And here the empty link is presented by A1 to the 0, A2 to the 0, and A3 to the 0. But by using Chebyshev polynomial, we can find another family of generators. But here, Chebyshev polynomials of second kinds are defined by the same some recurrence relation. Snx is equal to x Sn minus 1 x minus Sn minus 2 x, where S0x is equal to 1 and S1x is equal to x. Then easily we can see that the multiplication of Chebyshev polynomials with variables A1, A2, A3 forms the basis for genus 2 for the K-best-SAM of genus 2 antibody. And now, since we now understand the generators, let's start to find the relators. Here we have one proposition. For a three-manifold M with boundary, let gamma 1 and gamma 2 be disjoint simple closed curves in boundary M. And let's let glue two handles to M along gamma 1 and gamma 2 and denote the result three-manifold by N. Then, and let's denote J1, denote by J1 the submodule of this K-best-SAM generated by handle sliding along gamma 1, and denote by J2 the submodule of this K-best-SAM generated by handle sliding along gamma 2. Then the K-best-SAM of resultant manifold is isomorphic to the quotient module of the K-best-SAM of M, quotiented by J1 plus J2. And in our case, since our two closed curves are disjoint, so by applying this proportion, we can get such a result. The K-best-SAM of M is isomorphic to the quotient module of K-best-SAM of antibody, genus 2 antibody, quotiented by J1 and J2. Then we can find J1 and J2 independently, and we just sum up them. So to find the Jm, let's use the notion of relative K-best-SAM. Let's consider the second surface, more precisely the second disk with two holes. And let's take two framed points here and here, and let's note U and V. And its projection looks like this. Then it is not difficult to see that any relative curves connecting the points U and V is of the form CMN, where which is presented by this. Here, roughly speaking, CMN is the curve connecting U and V such that it rotates along A3 n times, and then along A1 m times. So for example, here for 1, 1, firstly, we rotate along A3 once, and then along A1 once. And so we can say that the relative Hebesem of these three manifolds with framed points can be generated by CMN. And now let's see the following situation. We are our goal is to find the JM. It means we want to understand L minus SL comma 1 L. Then let's think, let's disconnect, put U and V on gamma 1 like this. Then, sorry, we can separate it to gamma alpha 1 and alpha 2. Then for the link L, the handle sliding can be understood like that. If original link is this one, then the link after handle sliding is this one, SL, gamma 1, L, and this one is L. And both of them can be obtained by connecting two framed points like this and like this. And we are interested in the difference of them. So let's define the linear homomorphism from relative KBSM of this relative KBSM to handle body, KBSM of handle body. Then it is known that the image of the general basis of relative KBSM generated J1 like this. And now we denote the image of CMN SQ A2 by CMN SQ A2. And now we can get such a formula for CMN SQ A2 for positive MN Q. And of course, MN varies for possible integers. So m minus n is this also calculable. Then simply we can calculate like this. Then we can say that J1 is generated by such a letters. And similarly, by symmetry, we can say that J2 is generated by C bar Mn SQ A1, and it has such a formula. So simply we can say that the KBSM of this three manifold is isomorphic to the quotient module of the free module generated by the family of this multiplication quotiented by J, where J is generated by those two formulas. Then the question is, actually in the beginning, we showed that such a good decomposition of KBSM of S1 times S2. Then the question is it possible to get such a good looking decomposition for these three manifold? Actually, frankly speaking, in the beginning, I expected that because it is nothing but connected some of them. But actually, we can see that it is not. That is about the non-splitness. So our result is that there was such a conjecture that
Excuse me,
closed,
you have 1 minute. Can
Yeah,
you
yeah, I
please go
can-
to the
yeah.
concluding
Yeah, okay.
part?
I can finish within 1 or 2. So we wanted to such a decomposition, but we can show that it is not. Yeah, it is not. We cannot decompose the KBSM of these three manifold in such a good looking, because roughly speaking, from C11, we get such a later. Yeah, sorry. Here, that's such a later. Minus a to the 4 plus a to the minus 4, a1, a2, s3 plus this one. It means this one and this one are same in this KBSM. Why it is important? Because since this part is, roughly speaking, connected of those S2 times S1 and S2 times S1, and A1 is generator over here, and A2 is generator over here. But roughly speaking, they are not independent. So they are in this KBSM, they are mixed. And from A1, A3, you can get A2. Similarly, A1, A2, A3 goes to A1 like that. So they are the generators of our KBSM can be changed to others by multiplication. So roughly speaking, because of such a reason, we can show that we cannot get a good decomposition for our KBSM. Oh, okay. And that's all of my talk. And thank you very much.
Thank you. Let us thank the speaker. And we again have time for one short question. Does anybody have it? I have a question.
Yeah.
So usually KBSM
Mhm.
of a manifold is not a goal. It is a useful tool for proving some conjectures, some problems, for solving problems. So what is your final goal when you calculate this KBSM of this connected sum?
Firstly, of course, the first part is that it is known that the torsions of the existence of torsion of KBSM is related to the existence of non-separating spheres geometrically. But the question is, what is the torsion element? And what is the corresponding link in three manifold? And usually is where is. So we try to understand such a geometric meaning after this calculation. And for that, firstly, we try to understand the torsion element. But unfortunately, we couldn't get, we found the, how to say, the elements which can be killed by some torsion, some coefficient, but we cannot say they are literally torsion generators. So, but our final goal is that.
I see. So let us thank the speaker again.